Okay, so area and volumes of solids. Explain the relationship between the ratio of similarity, area ratios, and volume ratios of similar figures. We've already done one-dimensional and the two-dimensional version of this. Today we're just expanding to 3 dimensions. Put up fingers in the air, please. How many sides does a hexagon have? Fingers in the air. How many sides does a hexagon have? Hexagon, thanks for putting them up. Good. I just think hex has an X in it, right? So 6 has an X. That's all I remember. Hexagon, 6. Okay, so, for example, 1. Oops. We're going to try to make this a regular hexagon, which means all sides are congruent. Close. So when you draw yours, try to make all sides congruent for the regular hexagon. And there's another little one. Again, regular hexagon. And the base here is 7 feet and 5 feet. Okay, and we're given that these 2 hexagons are similar. Can anyone tell me what the similarity ratio would be for these 2? I know it. We've already learned similarity ratio. Sure, I like it that order that Arbor said. I like the bigger one on top, and the smaller one on the bottom. That way, in case it divides out nicely. Essentially, you take 1, which is A, divide it by B, and just make sure it's simplified. So the similarity ratio is 7 over 5. So for every 7 feet on the larger one, there's 5 feet on the smaller one. Okay, now we're going to write the perimeter ratio. Raise your hand, because we know this is a regular hexagon, so all sides are congruent. Who can tell me the perimeter of the big hexagon? Hmm? 42? Who agrees it's 42? Or do we need to change it? Okay, Cassie, how do we get 42? 7 times 6. There's 6 sides, right? Okay, so 42 feet over. Now let's get the perimeter ratio for the smaller one. Danny?
30.
Because 5 times 6? Yep. Excellent. 30 feet. Now I believe it simplifies because I noticed they're both even. Okay, so Ariana, what could divide into both 42 and 30 to simplify that fraction? Styles, do you have a note?
No. 6.
Okay, so yeah, we can divide 6 into both. Okay, Eric, what is 42 divided by 6? And M, what's 30 divided by 6? So, what do you notice? It's the same as which other ratio? Similarity ratio. These are the same, and we learned that before. Perimeter ratio and the similarity ratio are the same. That's why I left this little space. It's also A over B. Simplified, though. Okay? Now, that's one dimension, because perimeter is one dimension. All you're doing is walking one direction, turn, walk one direction, turn, walk one direction. Okay? Because you're just walking on the outside. It's one-dimensional. two-dimensional, it's no longer perimeter. If we're measuring in 2 dimensions, it's not perimeter anymore, what does it change to? Area, yeah. Okay, so let's do, because hexagon's kind of difficult to do area on, I want to not make our life miserable, so let's do a circle. And a baby circle. Example 2, draw 2 circles, one larger, one smaller. So maybe this one's 6 inches and this one's 4 inches on the radius. Okay, we're going to find the perimeter ratio in this and then relate it to the area ratio in just a sec. What is the perimeter of a circle called? It has a special name. Circumference. Circumference. Okay, when you walk around the edge of the circle, that's called circumference. And it has a formula. Sheila, do you remember the formula for circumference of a circle? That's area, because the squared. 2 pi r. Yeah, those are commonly, it actually wasn't until a few years ago that I could keep them straight. Pi r squared has the squared, and area is usually squared, right? Or is squared. So the squared one goes with area. The one without the square is circumference. All right, let's write the similarity ratio, which is the same as the perimeter ratio. Well, let's find the perimeter of the large circle, meaning the circumference of the large circle. The formula for circumference is 2 pi r. Anna, 2 pi r off the large circle. What would the circumference of the large circle be? 2 pi 6. Good. So she plugs in 6, whatever the r is. Anyone else need a calculator? Well, it is the same as perimeter, right? They're both the same, so we can call it either way. Okay, I'm going to actually keep the pi in because I foresee something happening. Because we're going to have 2 perimeter ratios being divided. So I'm just going to do 2 times 6. Would you agree that this is the same as 12 pi? And then you can put inches there. Okay, I'm going to just leave it as 12 pi. I'm not going to multiply it. Can you put the phone down, please? Okay. Now, let's divide by the smaller circumference. The smaller circumference looks like we have a radius of 4. Noah, what would our smaller circumference be? Good, which would turn into how many pi's? Well, 2 times 4 makes how many pi's? 8 pi's. Okay? What happens when we do 12 pi divided by 8 pi? What? Well, 12, it would have to be 12 divided by 4 to get 3. What happens with the pi's? Pi divided by pi cancels out. That's why I said we're not going to type that in because I knew that that would cancel out. Okay, but the 12 and the 8 can simplify. They're both even. We can divide by 4 for both. Emmanuel, if we divide by 4, what ratio would we get? What do you guys think? Is that right? 3/2. Yep. Okay, perimeter ratio. And guess what? MS, I thought we were doing the similarity ratio first. Well, similarity ratio, wouldn't that just be 6 divided by 4, which is 3/2. So, again, perimeter and similarity are the same. Okay, now we're going to expand this into 2 dimensions. This is 1 dimension. Perimeter ratio is 1 dimension. And we've done 2 dimensions before, so let's refresh our memory. For an area ratio, Perimeter ratio is A divided by B. But the area ratio is no longer one dimension. Does anyone remember the relationship between the A and the B for area? Yeah, it's squared. A squared divided by B squared. So if you know the perimeter ratio or the similarity ratio, because they're the same, all you have to do is square them, and you would know the area ratio. Okay, so here I have 3. What's 3 squared? 9. Divided by 2, what's 2 squared? 4. Does this simplify? Nope, there is our area ratio. Danny? Put it in your bag, please. I don't want to see it on your desk. Okay? And also, by the way, so I said perimeter ratio is the same as similarity ratio. And it's also the same as the scale factor. SF I use for scale factor a lot. All 3 of these are the same. For every 3, I don't know what we're in, inches, for every 3 inches on the large circle, there are 2 inches on the small circle. You see that on maps all the time. Like in a geography book, is the map of the world actually as big as the world? Well, it's scaled down, and then it has a little scale that shows you like 1 centimeter is equivalent to like 1,000 meters, or 1,000 miles maybe. Maybe that's more realistic. Okay, so that's a scale factor. All right, any questions before we move into 3 dimensions? This is perimeter, 1 dimension, area, 2 dimensions. Okay, example 3. Since our circle is not 3-dimensional, we have to do a new shape. Well, it would make a circle 3-dimensional. Now, a sphere is a circle that's rotated, right? If we rotate a circle, that creates the sphere. What if we just stack circles up? We get a cylinder. Okay, we're going to go cylinder because volume's easier. Okay, cylinder. Let's start with a small one this time. Small little cylinder. Big cylinder. Okay, we have 10 and 5, 6 and 12. And the question is, are these similar? Well, if they are similar, then they hold our ratios. The perimeter ratio holds, the area ratio holds, all we have to do is square the perimeter, and we get the area, and then the volume ratio would hold. So, to recap, perimeter, or similarity, or scale factor, similarity, and I'm going to put SF for scale factor, is A over B. That's 1-dimensional. Area ratio is not A over B. What is it? A squared over B squared, because area is the number of squares you can fit inside the number of unit squares you can fit inside the shape. So, using some reasoning, volume ratio follows the same pattern, cubed. A cubed over B cubed. Okay, so if we can show that the similarity ratio would, and since this is 3-dimensional, we're going to jump to volume. If all we do is cube the similarity ratio, and we get the volume ratio works out, then they are similar. Okay, so let's start with the similarity ratio. The similarity ratio, you just have to find 2 sides that are corresponding. Either we can use both radii, because we know both of those, or we can use both heights. We can't mix and match. Okay, Benito, would you like to use the heights or the radii? The radii, okay? Let's make our similarity ratio then. Similarity ratio. Okay, A over B for one dimensions. You said radii, right? Okay, so Joseph, can you get the ratio of the radii? Okay, we can do 5 over 6. I like to put a bigger one on top just in case it simplifies. 6 over 5, but they both technically work. Does this one simplify? It's kind of bad. No, doesn't simplify. Okay, so this is one dimensions. The volume ratio, because this is a three-dimensional solid, volume ratio, what do we do with the 6? Cube it. So 6 cubes. I need some calculator help. 6 cubed. I know 6 squared is 36, but 3 dimensions, we have to cube. 6 cubed. Do you have it for us? $216. And 5 cubed, does anyone know that off the top of their head? 125. So what we're going to do is we actually have to calculate the volumes, put it into a ratio, and if it matches that, then we say yes, they are similar. Okay, so let's find the volume of, I'm going to put a sub L for volume of the large. Does anyone know the formula for volume of a cylinder? Okay. So what you do is you find the shape on the bottom. What's the shape of the bottom of the cylinder? Circle. Do you know the area of a circle? Remember, this is area. It's going to have the squared, so it would be pi r squared. Now it's a bunch of circles stacked up, which makes it tall. So the third dimension is what measurement? Times close. I guess you could call it length if it was tilted. Height. Yeah, pi r squared times height. That's the formula. That makes sense because we have a circle stacked up for a certain height. Okay, so fine. I'm going to keep the pi in because we're going to have 2 volumes. It's going to cancel out. Pi times, what's the radius of the large? 6 squared times the height. 12. Okay, I need just the numbers calculated. 6 squared times 12. Don't shout it out. Please raise your hand when you know what 6 squared times 12 is. Thanks for raising hands. 6 squared times 12. Okay, Nui, what did you get? Do we have a second on that? 432. And then we'll put pi, right? Okay, next do the volume of the small. I put a little sub s to remind myself that which one I'm working with. Volume of the small. So again, pi r squared times 8. Pi times the radius. Louisa, what's the radius of the small cylinder? So 5 squared. And Louisa, what's the height? 10. Okay, 5 squared is 25 times 10. Does anyone know that without a calculator? 250. Good job. And we'll put pi. 250 pi. What happens to the pi's? Pi's cancel. Take your calculator, please. Everyone open up calculators. We're going to simplify. 432 divided by 250. You can push enter if you want, but you don't have to. Do you remember how to simplify a fraction on the calculator? Eric? Go to math. Math is right underneath the alpha button. And then what's the first thing listed? Fraction. That's what we want. So you hit enter, enter. Math, enter, enter. And what so does it match? So are these 2 canisters or cylinders similar? Yes, because the similarity ratio in 1 dimension leads to the similarity ratio in 3 dimensions, and it works. So we say yes, the two cylinders, cylinder E, I can't remember, are similar? Cylinder, cylinder. It's an E. I've learned that I pronounce things differently than they're spelled, so it messes me up on spelling. Cylinder. Okay? Okay, let's try another one. We're going to do a three-dimensional rectangular prism. These are the ones that are fun to draw. You have to practice your art skills. Same question, are they similar? Okay, to draw a rectangular prism, the easiest way I found is you start with a rectangle, and then you offset a rectangle that's congruent, try to make it the exact same, and then, what do? Connect the corners. The corresponding corners, connect them, and I like to make the ones that are in the back more dotted so they're like see-through. Okay, this is 2, 5, and 5, but we need a second one. This one will be smaller. Again, two congruent offset rectangles. And then you connect the corners. 1, 2, and 2. Are these similar? Okay, so what should we do? Are these similar? What should we do? Look at the last example. What did we do first? The similarity ratio, which just means we just need to find one corresponding side. So if I choose this, 5, what does that base correspond to? The 2. There we go. Similarity of the large over similarity of the small. 5 over 2. Okay, that's one dimensions for us. Now what? Okay, cube it. So that would bring us into volume, right? 5 cubed, 125, and we've done 2 cubed before. 2 times 2 times 2 is 8. Okay? So we have to find the volumes, make sure it works and matches 125 over 8. So what's the volume formula for a rectangular prism? Yeah, length times width times height. Because again, what shape is on the bottom of the rectangular prism? Not necessarily a square, it could be, but a rectangle, and the area of a rectangle is length times width, because a rectangle is 2 dimensions. And if you stack a bunch of rectangles up, you now have a certain height, right? Stack a bunch of rectangles up, and it makes it taller. So length times width times height. Volume of the large over volume of the small. Okay, I think you guys can do it. Would you guys find the volume ratio for me? Finding the volume of the large divided by the volume of the small. And stand up when you know if it's similar or not. You have a formula, length times width times height. You do it once for the big box, once for the small box. Divide them and see if it matches 125 over 8. Stand up when you know if they are similar. So the volume of the large. Okay, volume of the large. You should have just taken these three, lengths, widths, and heights. By the way, lengths, widths, and heights are always 90 degrees to each other. So if you ever see a diagonal, especially like on a triangular prism, you never use the diagonal for volume. Unless it's, well, no, that wouldn't even be a diagonal. Okay, so always use the ones that are perpendicular to each other. 2 times 5 times 5, and the other one's 1 times 2 times 2. And originally, before you simplify, what fraction did everyone get? 50 over 4, exactly. Which simplifies to 25 over 2. Does that match? No. So what's our answer? No. No. These two rectangular prisms, I wish you'd write a good explanation, are not similar.
Right there.
Explain. Okay. One thing you probably noticed on your SAGE test, which, I mean, the CRT did the same thing. Lots of the problems on the SAGE test were like story problems, right? Wordy problems, have lots of words. Unfortunately, most people, that's their weakness. Lots and lots of people struggle with story problems. So, and if you're going to skip a problem on your homework, which one's the one you skip? Story problems, right? Yeah. Sad but true. So here's our story problem for the day. It's just, people just don't visualize it. There's just too many words or something, so it takes too much effort to actually read it, and then read it and translate what in the world is actually saying. Yeah, it's tough for everyone. Okay, here's our last problem, the story problem. A bottle is 10 inches high. A bottle is 10 inches high and holds 34 fluid ounces of milk. Capacity is 1 unit of measurement. We have length, we have weight, and capacity. We have two metrics, we have 2 units of measurement. The metric system measures length with like meters, millimeters, centimeters, kilometers, with meter attached to all those. How do we measure length here in the U.S. in the customary system? Inches, feet, miles, yards. Okay, that's how the two differences of length measurements. Then weight measurements, we measure in like ounces and pounds, right? What does the metric system measure weight in? Grams, because they're more looking at the mass. Grams, kilograms, milligrams, so it always has that gram attached to it. And then the third category is capacity. Okay, we measure in fluid ounces. So if you oftentimes look at a bottle, it's in fluid ounces, and it's also in the metric system version. The metric system, they don't measure water with grams or meters. What unit measurement do they use? Liters, milliliters, kiloliters. Liters has that L attached to it, liters. Okay, so for us it's fluid ounces. A bottle is 10 inches high and holds 34 fluid ounces of milk. Remember the old milk bottles? Glass bottles you see in movies that are like delivered to the people's houses. I think Winter Dairy also still does that. To the nearest 1,000 ounces. Oh, there's a building that we're going to draw a picture of. That's given to us. So here's the top of the building. Windows. Little curtains to match the roof. Okay, maybe I didn't draw it that well then. What's it supposed to look like? Yep, it's the shape of a milk bottle. So there's our person. Obviously the person is smaller than the building, right? So we have a building that's in the shape of a milk carton, and we're given that's 480 inches tall. Okay? To the nearest 1,000 ounces, how much milk could the building hold if we closed the shutters, made sure it wouldn't leak, poured milk in it? To the nearest 1,000 ounces, 480, yep. To the nearest 1,000 ounces, how much, I guess that should be fluid ounces, how much milk could the building hold? To the nearest 1,000 fluid ounces, how much milk could the building hold? Well, the definition of similarity has a few stipulations. Number one, all angles are always congruent. If two figures are similar, the angles are congruent, the sides are proportional. And number two, similarity figures are not necessarily the same size, but they have to be the same shape. Okay, we actually have two objects here. All of the other problems we had two pictures. I've only drawn one picture of the building. What's the other object that was discussed in the problem? The smaller, the life-size bottle, right? The normal bottle. Okay, are they the same shape? Are they both milk bottles? Yeah. Obviously not the same size though, because one you could hold in your hand, the other one's a building. So we can deduct from that they are similar and apply the properties we know from perimeter, area, and volume. Fluid ounces? It's actually a lot more than that. Yeah, you'll be surprised. Okay, so let's again start off in one dimensions. For both the bottles, maybe we should actually draw the smaller bottle. Here's my smaller bottle. Because story problems, it's great to visualize what we're actually talking about. Now, I'm not drawing this to scale because I can't draw that small. So that's the handheld bottle. Mo, hi, how you doing? It's a milk bottle. Yeah. My grandma was a painter. Are you saying my artwork's bad? Well, where are you supposed to be? I think you're supposed to be somewhere. Guys, how tall is that milk bottle? 10 inches. And what else do we know about this milk bottle? What else do we know about this milk bottle? It holds 34 fluid ounces. Now think about when you put milk in a bottle. If you pour milk into a bottle or even a cup, does it expand out flat two-dimensionally? No. Does it expand out three-dimensionally when you fill a cup? Yeah. So what have we been talking about that's three-dimensional? Perimeter, area, or volume? Volume. So the volume that can fit in there is 34 fluid ounces. We don't know the volume of this building. That's what we're asked to find. Okay? So when you look at both the pictures, the regular size bottle of milk and the building size bottle of milk, we need two corresponding sides that we know the measurement of both in order to write a similarity ratio. So what would you call, what is 480 and 10? The heights. We know both heights. So you always have to use corresponding ratios to make sure you're finding similarity of the large, similarity of the small. 480 over 10. Those correspond to each other. Okay, I notice the zeros cancel out. So it's just 48 over 1. Which again is a scale factor for every 48 inches on the building, which is what, 4 feet? 48 inches on the building, there is 1 inch on the little bottle. Okay? Now what? Volume ratio. Okay, let's do it. Volume ratio of the large over volume of the small. Do we know the volume of the large? Nope. Do we know the volume of the small? Okay. Well, shoot, we don't know the numerator. Our end goal is to find the volume that could fit inside the big one, the building. How can we find that? Huh? Do we take 48, which is one-dimensional, and times it by a three-dimensional 34? Oh, getting warmer. 48 cubed, because we want volumes three-dimensional. So we're going to cube those. Let's see. The volume ratio should turn out to be, what is 48 cubed? Oh, big number. 110,592. And this one I can do, right? 1 cubed. Oh, 1 times 1 times 1. Do you agree with me that that's 1? Yeah. All right, so if well, we were given that they're similar, so they should hold a proportion. The proportion is 2 equal ratios. Okay, so we have this is what the volume ratio should simplify to, and we have this has the missing volume, but they're both volume, and they're both a ratio. So if we set them equal to each other, we can find the missing part, because the proportion is 2 equal ratios. X over 34 equals that big number over 1. They're both volume. That's why we can set them equal to each other. Any questions here? We don't actually divide. If we use inverse operations, this says divide. If we're trying to get x by itself, we have to use, so we times. Or if you do like the fishy method, that's timesing, right? Times by 34, and this problem's nice because we have a 1 in the bottom. Okay, can you simplify x? Raise your hand when you know how many fluid ounces can fit inside of the building. Actually, let's put equals first. Manual, times those out, please. Amy, do you have it? What? Yeah. Okay, can you tell me the numbers? 601 what? 28? Okay. 3 sevens, right? Okay. Where do I put commas, Amy? There? Okay, now the directions actually said round to the nearest 1,000. Okay, so here's your thousands place. The 1 is after it. 5 or more, up the score. 4 or less, let it rest. Should we up the score of the 0 or let it rest? Let it rest. So we get 3,760,000 fluid ounces. That's rounded. It's the nearest 1,000. Is that a lot of milk? Yeah, that's a lot of milk. Yeah, a lot of cereal you go through to use all that milk, huh? Okay, the homework begins on page 602, I think. Yes. Page 602, we're doing numbers 1 through 13. And then there's a box I want you to fill out. 23, oh, not 13, 12, sorry. 1 through 12. One last problem. And then the box is 23 through 26. Let me give you a hint on the box. It has 3 columns. The first column represents one-dimensional, A over B. The second column is two-dimensional. Those are all squares, right? And then three-dimensional. Now, if you're given the three-dimensional and you're trying to work backwards, say we're given 125 out of 8, and you have these as blanks, it's easiest to always go back to the one-dimensional. If this is cubed, how do you go undo a cube to go back to one dimension? Cube root. So you'll take the cube root. What number times itself 3 times is 125? 5. And cube root, what number times itself 3 times is 8? 2. And then 2 dimensions, we just square that. 5 squared is 25. 2 squared is 4. Okay, so if you have to work backwards, you take the cube root if you're in 3 dimensions. If you're in 2 dimensions, you take the square root. There's your hint for that box for number 23 through 26.